All right, this is my best attempt to draw a pyramid as specified in the problem. So you have this sort of four triangle structure with a square base, of course. And so I've labeled with different inks the different quantities that we're using here. So the height of the pyramid from tip to the base is h. That's pretty straightforward. S is half the side of the square base, and so this is s, and that is also s, and we're going to use that fact in a bit. And L is just the length of a square disk cut off from the pyramid. We're also going to be using incremental, infinitesimally small volume dz, and that will be in the z hat direction, obviously. And so now let's get started. The center of mass, the z coordinate, is what we're looking for here, because center of mass will be 0 for the x and y coordinates. So the z coordinate of the center of mass is given by obviously the integral of z dm over the total mass m. Now total mass m is of course the infinitesimal, the sum of all the infinitesimal masses. So this is integral of dm. And so if you'll remember, dm is just rho times dv. So we're replacing that here. So this is z rho dv over rho dv integrals for z of cm. Okay. Next, we find out what dv is. So dv for an infinitesimal volume element will be height dz times the length times the area, which will be L squared. That's the whole point of using L here. And so L from the diagram is actually S over H times H minus Z quantity squared, H minus Z. And so we square that and multiply that by dz. So that's your dv. And then S, we don't know what it is, but from the Pythagorean theorem, I'm just going to say Pythagoras, you have here, let's call it A for this hypotenuse, in the square down below at the base. So A squared will be well, S is the whole side, right? So S is the whole side, which means A squared will be S over 2 squared plus S over 2 squared. Okay, why do we care about A squared? Because we want to use the Pythagoras theorem again, this time to find H squared. And so by the Pythagorean theorem, side S, which is the side of the pyramid, the length of the side of the pyramid, S squared will be equal to H squared plus A squared, and this is where A squared comes in. So this is H squared plus S squared over S over 2 squared plus S over 2 squared, making it S over 2 half when you add them together. So therefore, H becomes S over square root of 2. All right, now we're in a position to try and tackle the integral. So ZCM is integral of, is just that. So it's so we're going to pull rho outside. It's a constant. Rho times the integral of z times L squared dz over integral over rho times integral of L squared dz. Right, and so the rho's cancel. And then we're going to plug in what we know L squared to be, or L squared dz to be. So that's so let's see, z times L squared, which is S over H times H minus Z, quantity squared times dz over S over H times H minus Z quantity squared dz. And we're evaluating these integrals from 0 to h, obviously. Therefore, let's see what that simplifies to, so that the numerator is the integral from 0 to h of h squared z minus 2hz squared plus z cubed dz over the integral of 0 to h of h squared minus 2hz plus z squared dz. All right, so now I'm going to write down what the integrals come out to. So ZCM is 1/2 h squared z squared minus 2/3 hz cubed plus z to the 4th over 4, evaluated from 0 to h, over h cubed z minus hz squared plus z squared z cubed over 3, evaluated from 0 to h as well. And so you work out all of this arithmetic, or you plug in h and all these z's. What you get is h over 4. And h, remember, is s over square root of 2. So this is s over 4 root 2. So we have an answer in terms of s. Therefore, or I should say, therefore, the center of mass coordinates are, which is a vector, is 0 I hat plus 0 j hat plus s over 4 root 2 k hat. And that's it.